Other than the formal charge, there's a second way to count electrons that is not used for Lewis structures. However, it's a method to count electrons that will tell you how poor or how rich in electrons that specific atom will be. And that's important, for example, when you think of metabolism and digestion, when the kind of compounds that we ingest, they are rich in electrons, and what we exhale is typically CO2. We have to be able to know to keep track of electrons. And as I said, while this not may be the most common way to keep track of electrons in Lewis structure, it may be very important to keep track of where electrons are. So let's just try to solve this problem here. It asks you to identify the oxidation state of carbon in the following compounds. Well, how do we do that? The way to count the oxidation state of each carbon, unlike calculating the formal charge in which we assumed a perfectly covalent bond, that is, we split the bond in two and we shared the electrons equally for both atoms, in the oxidation state, what you consider is that all bonds are ionic and the most electronegative will keep all of the electrons. So the most electronegative of the element in the bond, will keep all the electrons of the bond. Okay, so what does that mean? Let's see. For carbon dioxide, I'm going fast here. If you build the Lewis structure of carbon dioxide, you'll have something like that. We know oxygen is more electronegative than carbon. Therefore, it means that when we see these two bonds in here, all of the electrons are being kept by oxygen. So how many electrons does oxygen have? Well, oxygen will have 1 pair, 2 pairs, 3 pairs, 4 pairs. It'll have 8 electrons. To be neutral, it would be 6. That means the oxidation state of oxygen in here is -2. The same for here, it's -2. So what is carbon left out? Well, carbon has no valence electrons. For a carbon having left out no carbon electrons, that means you have 4 left. That will be a +4. Okay, this means, so because the carbon has no valence electrons, it has given away, again assuming that all bonds are ionic, it has given away these 4 electrons. We say that the oxidation state of carbon is +4. Let's see for methane, carbon and 4 hydrogens. In this case, carbon is more electronegative than hydrogen, so in this case carbon keeps this pair, this pair, this pair, this pair. How many pairs does carbon have? It has 4 pairs, so it has 8 electrons. If it has 8 electrons, to be neutral it would be 4. It means it has 4 electrons of excess. That means that the oxidation state of carbon is -4. So it's quite a difference from the +4 to the -4. We will say that carbon in here is highly oxidized and carbon in here is highly reduced. Remember these terms for electrochemistry, but it's very important, electrochemistry, in the next semester. But it's important to understand that you can get a lot of energy from methane because this carbon has a lot of electrons. There are, of course, then compounds that are in the middle between the highly oxidized CO2 and highly reduced CH4. In this case, what we call formaldehyde, what is the oxidation state of carbon? Well, oxygen keeps, because oxygen is more electronegative, keeps these, but carbon keeps this pair. So how many pairs of electrons does carbon have? It has 2 pairs, that is 4 electrons. The oxidation state, because it already has 4 electrons, is neutral, so 0. And the last one for methanol, how how many electrons does carbon have, calculating them using the oxidation state method. Well, carbon is more electronegative than hydrogen, so it keeps these 3 pairs, but keeps none from the oxygen. So carbon has 3 pairs, or if you will, 6 electrons. That means it has 2 extra more. The oxidation state of carbon is -2. Okay, so we will say that, and that's because there's this alcohol group. So typically alcohol groups are more reduced than carbonyl groups, okay, because you go from negative to 0 and so forth. It's not a coincidence that when you ingest some fats or some sugars, you will follow this route. And the whole process of metabolism is removing electrons from the food that we ingest.